Go ahead, Peter.
Yes, thanks, Pasha. So as Pasha already introduced, I'll briefly speak a little bit about Ucx Pi, the progress in 2021. But before we address the progress status, let me give a very brief introduction of Ucx Pi for people who may be unfamiliar with it. Ucx Pi is a Python interface for Ucx, providing an object-oriented synchronous API and a high-level asynchronous API for writing concurrent code with Python's async or await syntax. No direct bindings are provided at the moment. Ucx Pi is intended to be a simple replacement for Python communications, such as sockets, and thus we provide a similar interface, but today it's not identical to the Python sockets one. Ucx Pi is targeted at library and framework developers, since Python users tend not to handle communication at the application level directly. Because we provide a high-level library, no UCX or C knowledge is required to get started with Ucx Pi. Just basic client-server communication understanding is enough. Today, the largest consumer of Ucx Pi is a framework for scalable analytics called Dask, and Ucx Pi is made available to users normally via frameworks such as that one. To give you an idea of how the Ucx Pi code looks like, consider these two frames being shown. On the left, we see the typical source for a simple server. The main coroutine just creates a listener and registers the server coroutine as a callback. It then waits until the listener is closed. The server coroutine allocates an empty buffer, empty CuPy buffer that is an array backed by CUDA memory. We then receive data from the remote endpoint on that array and send the same data back to the endpoint. This is all using tag messages. The client side shown on the right creates an endpoint that connects to the server's listener, then creates a CUDA array filled with zeros. Following that, it then performs the message transfer in reverse order. Send the array data and receive the data back on a new empty CUDA array. In the previous slide, we used CuPy to send and receive messages using CUDA memory, as it implements the CUDA array interface protocol. However, it's possible to replace that with other array types that implement the CUDA array interface, such as RMM, or other libraries supporting the host memory protocol array interface, such as NumPy. So any library that supports either array interface or CUDA array interface can be theoretically plugged in to be used with Ucx Pi. This is a plot I've shown already last year, but this is just to put in perspective the benefit of using Ucx Pi in Dask. On the left, we see a workflow with the default Python sockets communication in Dask. And on the right, we see the same, but with Ucx Pi. In both cases, red represents communication. With Python sockets, we see communication dominates runtime. But although communication is not negligible, even with Ucx Pi, it greatly reduces the total runtime. So this is an overview of the Ucx Pi progress in 2021. We'll go into more detail on each of those points and a few more in the next few minutes. Some of those were improvements exclusively on Ucx Pi side, but others were improvements that Ucx introduced and Ucx Pi can now leverage. TCP SOC-CM was introduced in Ucx 1.10 as a complete replacement to the former TCP implementation from Ucx 1.9 and older versions. but many bugs still existed prior to UCX 1.11, and we've worked with the UCX team to resolve all those issues. And as of UCX 1.11.1 and newer, there are currently known bugs that impact UCX Pi. The whole UCX team has been very helpful in addressing issues quickly, but here I would like to especially thank Dmitry Gladkov, who worked with the Ucx Pi team very closely for countless hours in 2021 to address all issues in the quickest way possible. Thanks a lot, Dmitry. Besides the issues that we've encountered, some features that were important to Ucx Pi users were also missing in the new implementation. One such feature was Tcp Loopback Support. TCP is a very important transport for Ucx Pi users. One important use case is when using NVLink for intranode GPU communication, but only TCP is available for internode communication. This is a more common use case than many of us would think or even hope for, but it's a necessary evil for large Ucx Pi customers and frameworks such as Dask. This isn't limited to Ucx Pi or Dask though. Other frameworks also rely on TCP when more efficient interconnects are not available. For example, NVIDIA Morpheus, which is an open AI framework for cybersecurity providers who consumes UCX directly in C, it also relies on TCP. So to summarize, I would like to say that TCP is perhaps one of the least performant transports in UCX for obvious reasons, but one that we can't afford to neglect. Therefore, we will continue to test it heavily, and we really appreciate everyone's support in its continuous maintenance and improvement in UCX. With UCX, it's possible to register an error callback for each endpoint. Prior to UCX 1.11, some transports didn't support them, limiting their usability. For example, if CUDA IPC was requested, at the same time an error callback for that endpoint was registered, the transport would be disabled completely, thus causing performance to suffer quite a bit. Previously, Ucx Pi implemented its own connection closing mechanism, but this would depend on the underlying transport to handle errors as well. For example, when using InfiniBand, the process would often hang indefinitely if closing connections could not be done on time. Error callbacks are much more versatile though, as they prevent such strange patterns, allowing us to handle both connection errors and normal closing as a single step, while avoiding some of the issues that were not possible to be handled at the Ucx Pi or application layer. As of newest Ucx Pi releases, provided Ucx 1.11 or newer is used, endpoint error handling is now default, which enables graceful error and connection closing handling in Ucx Pi. For users usually accustomed to more high-level frameworks, tag matching can often feel like an kind of extraneous addition to exchanging messages between peers. In Ucx Pi, we made the interface a bit more palatable to those users by pre-assigning random tags that are exchanged between endpoint pairs at endpoint establishment time and then used throughout their lifetimes. However, this is only available in the asynchronous API, whereas when using the core API, the user is responsible for managing tags in the application. With the introduction of active messages, Ucx Pi can now provide a more familiar interface to Python users in both asynchronous and core APIs. In addition to that, we can avoid tag matching overhead, as existing Ucx Pi applications don't make use of that feature today. With active messages, Ucx can also pack metadata in the message, simplifying the receiving interface by releasing the requirement for identifying whether the receiving object is CUDA or host memory, as well as having the message size already known at the receive time, and thus capable to automatically allocating the receiving buffer, calling the user registered allocator. Because buffer allocators support the array interface, CUDA array interface, or Python buffer protocol, the received buffer can be converted to a different object type with zero copy when the destination object has the same type. So there shouldn't be too much overhead in doing that. This is the same slide I presented in the beginning of the talk. It shows Ucx Pi sending a NumPy array on the left and receiving it on a new pre-allocated NumPy array on the right. Notice here that the array to be received needs to be pre-allocated with correct size and type by the user to be received via tag message. However, with active messages, we now do it a bit differently. The sending side remains the same, except that the name of the method is now amSend. The receiving side, though, has to register the allocator for both host and CUDA memories. And when a new message is received with the amReceive method, it will then use the correct allocator depending on the memory type being host or CUDA. So the allocation of the resulting message is done automatically by Ucx Pi. By default, Ucx Pi uses a byte array as the allocator for host messages and has no CUDA default allocator. So we pretty much pass the responsibility to register the preferred CUDA allocator to the user, if, of course, one is necessary. Please note that the active message API is still experimental and subject to change. The new remote memory access feature allows direct access to local memory from a remote worker. The user may choose to allocate memory buffers specifically for use with the remote memory access feature of Ucx Pi, but it's also possible to allow the underlying memory of an existing Python object, such as a Python byte array or a NumPy array, to be mapped for remote memory access. In addition to that, the Ucx IO class extends the RMA capability of Ucx Pi with an interface that simulates Python streams. So we enable the user to treat a remote memory buffer similarly to a file handle. This feature is currently available on the core API only, and it was contributed by Matt Baker from ORNL. Thanks, Matt. It's now possible also to establish endpoint connections via IP-less setups in Ucx Pi. I understand this is a known capability for people involved with Ucx directly or low-level communication in general, but may be a foreign concept to some Python users. So let me elaborate a bit on that. Ucx Pi now provides functions to query the underlying Ucx worker's address. This address can be serialized as a byte string and distributed via some service that's reachable by all parties. For example, a DNS SRV record or a shared file system. With knowledge of this address, Ucx Pi can now establish an endpoint to the remote worker, even if it doesn't have an IP address assigned. But please keep in mind, this is only possible for some interconnects such as InfiniBand. Although the same feature of establishing connections with a Ucx worker address can be used even for cases where there are IP addresses assigned, and when the user needs to use that, but it prefers to rely on Ucx to provide the worker address without having to worry about the IP address or ports and so on. So finally, unlike the regular client-server setup, that most Python users are familiar with, a listener in this case is not required, but only endpoints on both participating processes. The separation of core and asynchronous APIs has been consolidated now, avoiding circular dependencies. This now means the asynchronous or high-level API now depends on the core API, but the core API is entirely self-contained. They are currently shipped together, but we will consider shipping them separately if necessary. And this may be required during the upstreaming of Ucx Pi code base into the Ucx main repository, which we'll address later. The Python code has also been better organized, separating components into their own files. Because of Python's limitations, we still need to maintain a main file to include the source code file of each component, which allows us to maintain a single Python extension then. Each Python extension leads to a new shared library file, but because Ucx Pi codebase is not that large, it doesn't make a lot of sense to break binaries down into several smaller shared files, which would also increase the total binary size. And for that reason, we decided to keep it to a single Python extension, including each component's source file then. Regarding documentation, we added Docker-specific information about NVLink, as well as some details on common operating system limits, such as maximum file descriptors and maximum number of connections open, which often confuse users in the Python world. Dask documentation has been removed and lives only in the Dask CUDA docs page now. And it contains also some better examples than it did before. Also, some users had questioned us on details to get started with Ucx Pi or deploying applications with it. So to address those questions, we now include recipes to create a reference Docker container. After creating a Docker container using the recipe, the user may run all Ucx Pi tests and benchmarks. However, this is today still limited to basic memory and transports only. So there's no CUDA or MoFed support for that currently. We also set up a simple CI that is capable of running tests on multiple Ucx versions and multiple transports too. Currently, we run the latest stable version, that's 1.11.2, the upcoming release branch, which is currently 1.12.x, and the master branch each night. The tests execute on an NVIDIA DGX1, supporting CUDA memory alongside of host memory, as well as NVLink and InfiniBand, in addition to most of other system interconnects that are common in most systems. The CI has possibly been one of the most important things we worked on this year. It allowed us to quickly find several regressions in Ucx, Ucx Pi, Dask, both on functionality and performance. As an example, the plots shown on the right represent bandwidth of RC and CUDA IPC transports during the Ucx 1.12 development cycle, even though the exact dates where some regressions may have happened weren't captured, as you can see by some missing data points. The dips in the plots gave us a good idea of commit dates to bisect Ucx and identify the change that caused it to report them back to the community that were later on addressed. On the application or consumer side of Ucx Pi, we are also happy to announce that we are now entirely capable of leaving mapping of CUDA and InfiniBand devices to Ucx. This change considerably simplified code in Ucx Pi. In the past, we had to rely on libhwlock to determine the topological proximity between devices. Besides, this was mostly limited to bare metal configurations, and complex cloud systems weren't able to determine the correct mapping automatically, for example. Finally, RDMA-CM now successfully works with all known desk use cases. It used to be unstable and depend on several different variables in Ucx Pi and Dask to make sure it worked correctly in past Ucx versions, but this is now much simpler now. As we mentioned in last year's annual meeting, we still intend to get Ucx Pi upstream to the mainline OpenUCX repository. Unfortunately, due to delays that happened throughout the year, we were unable to complete it. The good news is that we began some of the work already. We have opened PR 7412 that introduces Ucx Pi tests in OpenUCX's CI pipeline. Due to some limitations, such as the lack of CUDA support in CI, we're still in the process of working with the OpenUCX team to get infrastructure set up to provide all necessary capabilities before it can make its way into the mainline OpenUCX repository. We hope that perhaps after the 1.12 release, when things get a little calmer, we'll be able to complete that. Once testing is supported and integrated, we'll be able to upstream Ucx Pi source code. Earlier this year, we also had a meeting with the OpenUCX team regarding this process, and we are in agreement on how to proceed. As a high-level overview, we'll first upstream the core library that is composed of the Python and C code, followed by the asynchronous or high-level library, and finally, we'll work on the packaging situation. We don't have much time to address Python packaging in this presentation, but since Python users tend to rely on different package managers than those offered by Linux distros, we'll probably need to address those as use cases arise. Today, we only publish Ucx Pi binaries via Conda packages in the Rapids AI and Rapids AI nightly channels. So if you plan to use Ucx Pi in your application or have any questions regarding binary distribution, please feel free to reach out to us and we'll attempt to work out solutions for your use case. For 2022, we have a number of improvements planned. I'll briefly go over a few of them here. As you may know, the standard Python interpreter is single-threaded, and similarly, Ucx Pi has been written in such a way. However, it's possible to resolve that by carefully planning which parts of the code will release the Python's GIL or global interpreter lock, and this should enable Ucx Pi to support multi-threading. When using the core API, this should already be possible, but the user in the core API, the user is responsible for progressing the Ucx worker. So although this is theoretically possible, it's untested today. Progressing the Ucx worker in the asynchronous API is done by an internal Ucx Pi mechanism, and that doesn't expose any control to the user, and it needs to be reworked to permit multi-threading to function correctly. One of the main weak spots of Ucx Pi today is the transfer of small messages, often smaller than 1 megabyte in this situation I'm referring to. They can be up to 5 times slower than a pure C implementation based on the UCP interface, and we definitely need to improve it. Some applications may still require Ucx TLS to be set to function properly. The primary reason behind this is that Ucx identification of closest CUDA and InfiniBand devices can only work if the process has created the CUDA context prior to the initialization of Ucx. Because of that, we are forced to make the user specify when CUDA devices will be used in the application, for example, in Dask, to make sure that the context is indeed created before UCX is initialized. If that isn't done, GPU direct RDMA won't be enabled, and these may have a steep negative impact in performance, depending, of course, on the communication patterns of the application. Ideally, UCX would not require the CUDA context to exist before its initialization, and it's my understanding that this is already being worked on in UCX. So once that's done, we can completely rely on the default UCX TLS configuration, which will make UCX integration as seamless as possible. So finally, if you have any feature requests, please feel free to reach out to us on GitHub via the link you see in the slide. Let me also remind you that everyone is welcome and encouraged to contribute even today before it's upstream to the open UCX main repository, but we expect to have even more engagement once the upstreaming is complete. And that's all I had. Thank you for listening to me, and I'll be happy to take any questions now.
Thank you, Peter. Any questions for Peter about Ucx Pi? The only question that I had, Peter, and you answered it, is about release plans. It was well covered.
Yeah, release, we expect that once we upstream with Ucx Pi, with the open UCX main repository, we will then follow the same release schedule as UCX. And packaging, as I mentioned before, it will depend on probably a use by case scenario.
Excellent. Yeah, I want to comment, by the way, active message Pi interface looks really nice. Seems like much more convenient than dealing with tags.
Yeah, it definitely is. We are still implementing a few more features, for example, that the user can register its own callback, but that's still under work. So, yeah.
So just to clarify, when you mentioned that active message interface is experimental, you meant it's support in Ucx Pi, not in UCX, right?
Yes, in Ucx Pi. So I don't expect that to change too much, but you never know. It's still, we are still testing it. Honestly, I haven't been able to test as much as I wanted to. So if we find issues with it, we may still have to change things there, but hopefully that won't be necessary. It was more of a disclaimer actually than anything else.
Okay, just last year we are actively working on it. I mean, on extending active message interface. And it would be very good if you have any feedback. For instance, if you see anything is missing from the API perspective, or you think something can be added, please raise an issue in GitHub.
Yeah, I think I have one issue that's, we can sync offline, that's regarding using registering user callbacks, but this is definitely something that I just couldn't work more yet. So that's why I didn't push it further still.
Okay, we can discuss that offline.
Yes, thanks a lot, Michael.
There's one more question in the chat from Benson 8. Are there any other interesting use cases other than Dask?
We have another one. I'm not sure we are supposed to talk about it publicly, but there is one use case for it's going to be used in part of the management for UCM. This is part of the Mellanox management interface for InfiniBand. So this is one thing, but I'm not sure if I can go into much detail, to be honest. So there are, and we would also love to have more people interested in using Ucx Pi, but by far Dask is the biggest use case today, definitely.